Cong Yan. He will give a presentation of analysis of biped robot on uneven terrain based on feed-forward control.
Okay,
So,
can you hear me?
yeah, I hear you.
Okay, please allow me to replay the video of the presentation. Hello, everyone. My name is Cong Yan. Today, I would like to talk about our work. The title is Analysis of Biped Robot on Uneven Terrain Based on Feed-Forward Control. Fumihiko Asano, Yanqiu Zheng, and I from Japan Advanced Institute of Science and Technology. Longchuan Li from Mekong University. Compared to using complex feedback control to achieve stable gait, limbed cycle dynamic walking such as passive walking has been widely studied as an effective approach to realize efficient walking motion of robots. Although it has already been confirmed both theoretically and by experiments on actual machines that highly efficient dynamic walking on level ground is possible by applying the passive walking principle. From the viewpoint of practicality, it is an indispensable ability for robots to have the locomotion skills to adapt to uneven terrain. From the viewpoint of natural dynamics, it is desirable to have a natural and energy-efficient control method that utilizes the intrinsic dynamic characteristics of bipedal robots. Here, we propose an approach to apply a periodic fixed waveform control torque to hip joint without using feedback of posture information to stabilize the gait of biped robot. This figure is the model of semicircular footed compass-like biped walker on uneven ground. This walker has a waist with mass of mh, two identical rigid leg frame with mass of m1, m2, and length of L. In addition, the legs have semicircular feet, whose radius is r. Here, let XC-ZC be the contact point of the slope with the ground, and XZ is the center point of the semicircular feet. Z1 is the angular position of the stance leg regard to vertical, and θ2 is the angular position with respect to vertical of swim leg. The U is the only possible control input is acted on the hip joint. Let Q be the generalized coordinate vectors. The robot equation of motion then becomes this, where M represents the inertial matrix, H represents the gravity terms, combination of the central force and Coriolis force. On the right-hand side, J lambda is the holonomic constraint. In addition, the driving vector is set as S. The velocity constraints of the contactor position of the stance leg and the ground on a non-slip plane are specified as the XC-ZC. Therefore, we can obtain the Jacobian J. The ground reaction force lambda is the simultaneous solution of equation of motion. The second-order derivative Q means the generalized acceleration. In this research, According to the inelastic collision model, the rear leg crawls on the ground immediately after collision, and the state transition is as equation of collision. Here, the superscripts minus and plus mean just before and after collision. The velocity constraint condition for the landing point of forward is determined as xc bar and zc bar. We can also obtain the ji. In this study, we use the feed-forward control, which is performed simply by specifying the control output as the default waveform, in order to smoothly influence the dynamics of the robot. The torque change of the output is set to the sinusoidal trajectory, where AM and FC are the amplitude and the frequency of the sine wave, respectively. The amplitude determines the magnitude of the torque applied to the control input, and the frequency is the speed at which the control input is applied. We choose the physical and control parameters as listed in the right table. Set the inertial conditions as Q and Q dot. Therefore, working starts from the state immediately after the leg colliders with enough kinetic energy. We set the slope angle to change randomly every 5 steps, and the max and mean angles to be 0.3 radian and minus 0.3 radian, respectively. The range of each angle change is less than 0.25 radian, and let the height of each swim legger at grounding be equal to 0. This animation is the simulation results with single feed-forward control, which enable the robot to perform the working motion and generate different gait by utilizing its own mass and gravity. The step length becomes larger when going downhill and the opposite when going uphill. The right figure shows the faceplate plot of the gate. It is found that, even without feedback control, given only a sinusoidal torque, the bipedal working robot can form multi cycle working gait. Here, the figure A is the center point position of the semicircular foot of the stance legger. The step length is influenced by the tilt angle of the ground and changers. B and C are the changes of the biped angles and the angular velocity. The last figure D shows the time variation of the vertical ground reaction force. Furthermore, we can see that the values always give positive. It can be assumed that the foot is not off the ground. These figures show the energy change with the control input. The top one indicates the total mechanic energy, and instance immediately after the feet collision, we can see the consumption of kinetic energy as shown in bottom figure. Except of the first 2 steps, the amount of energy consumed afterwards is very low. Experiments should be conducted to verify the validity of the results of simulations so far, The CAD design of the biped walking robot is showing the left figures. Since the compass-type biped robot has no knee joint, the three motors on its legs are not directly involved in the forward walking moment of the robot. In addition, at the waist, the motors at the hip joint use the planetary gear mechanism to move both legs against each other. The developed experimental apparatus is showing the right figure. Here is the video of the inertial experiment. We can see that the robot can work successfully on flat ground with only feed-forward control input. In the future, we will optimize the control waveform and the foot curvature of the robot so that the biped robot can successfully challenge the angled ground. In this study, we showed through numerical simulations that it is possible to generate the gait on the uneven terrain with single feed-forward control. We also explored the appropriate periodic torque control can take full advantage of the robot's own dynamics. Finally, in order to verify the rationality of the simulation, we designed and built a bipedal walking robot machine. In the future work, experiments are conducted on the actual machines to confirm the difference between the real environment and the simulation. It is also necessary to select an optimal detection method to measure the gait date. Thank you for your listening.
So thank you very much for the presentation.
Thank you.
So we have
very much.
also time for some questions.
Yes. Can I ask questions?
Yeah, please start.
Thank you. And I have a question. The first one is, I have noticed that your robot is used in muscular feet. And can you tell me the reason that you use it? And the second one is the experimental successful work every time? I mean, sometimes
Cannot hear you.
the robot falling down or other things happen. Thank you.
Okay. Okay. Do you mean the semicircular foot or the why we use the semicircular foot?
Yeah, can
Okay.
you explain the reason that you use the philosophy?
Okay. Because the virtual ankle joint torque can be generated, and also the energy loss at the time of the impact with the swim leg can be reduced. Also, the energy efficiency can be improved. Okay. About
Yes,
hi, yeah, about the second question, do you mean that the experiment the successful every time?
yes.
Because we use the feed forward control without any feedback control. The only single feet forward control in the hip joint. The requirements about the inertia stage is very high, and not every experiment can be successful. Also, in the future, we will keep optimizing the input waveforms and strive to improve the robustness of the robot.
All right, thank you.
Thank you very much. Excuse me? Can I close the screen?
Yes, please stop your share screen.
Okay, thank you.
Professor Bells, please please finish this session.
Okay, thank you.
Professor Baron. It's me, Professor Baron. Professor Baron. I don't know why, but Professor Baron is not connect. So does not connect. So let me close this session. Thank you very much for all presenters and all audiences. Thank you very much. So next session will start 7:15 by UTC and 4:15 p.m. in Japanese time. So see you in next session. Thank you very much.